So let's understand the Biot-Savart law by doing the following example. In this particular example, what we want to do is we want to find out what is the velocity happening in this at this location here. To find the velocity here, we want to know the influence of each one of these guys here, each one of these segments. And note that since the velocity is going down, using the right-hand rule, we know the direction in which the direction I'm going to take is, the arrows give me that direction, right? Because if you use the right-hand rule, that's going to point a velocity going downwards. Okay. So this is best done by dividing this into rectangle. Okay, so I did that. I divided the whole thing. And we can see that the distances are 4. This is 6. This is 5. This is 5, 6, 4, 5, and 5. So that's given from the problem. And we're going to further divide this in triangles. Why I want to divide in triangles? Well, note first of all, this we found in our class lectures. Okay, so we know that the class lectures, we found that if we have something with the same angles, okay, in theta 2 are identically 0. So I'm really taking, I am not considering this part right here. I'm just considering this big triangle. Then you can show that theta, your velocity at this point coming downwards, a function of theta 2 is given by this. We also derived in class the following expression, where we said that if you only want to find what is the velocity because of this segment, but based on this angle, alpha is given by this. Now, if I wanted to know what the angle theta 2 was only, depending if angles were different, then it was given by this expression right here. Okay, so that's information that we know. And so the next thing we're going to do is we're going to divide this in a bunch of triangles. And I did that. And we're going to give each one of these segments a different, so we're going to call this 1. We're going to call this segment 2, 3, 4, 5, 6. You wonder why I gave the numbering system. Is rather arbitrary, the numbers that I gave. And just from the previous chart, this is 5, 5, 5, 6, 4, 5, 5, and this is segment is 4, this is 6. And because this distance is, this angle and this angle are identically the same because the distance here is the same. Here, this angle and this angle is the same. However, the angle here, the angle located here is not going to be the same as this. Okay, this is alpha, this will be a beta because the distances are different. And the same here, this is beta and this is alpha. So the angles, so I need to use different rules for that, right? So total velocity v would be the influence of total velocity calculated there is the influence of the segment 1, then is the influence of segment 2, plus influence of segment 3, plus influence of segment 4, plus the influence of segment 5, and plus the influence of segment 6. So each one of these segments is going to contribute what is the total velocity there. Okay, so let's work one segment at a time and see what the contribution of those velocities is. So the next item we're going to go is item number 1. And this segment here, let me change the colors quick. What you have is, this is 5, this is 5, and this is 6. This is the angle that I'm looking for. And this is theta 2. This is angle theta 1. And the velocity Vp1 is equal to minus gamma 2 pi cosine of theta 2 EP. Okay, and we want to know the distances here. So if you need to know the angle, you know this is use Pythagorean theorem. This is 25 is equal to square root of 61. So cosine of theta is equal to adjacent over hypotenuse. This is 5 over square root of 61. So this is equal to, the problem gives me this is 200 divided by 2 pi. There's an h missing here. The distance from here to here is 6. This is the point. So distance is 6. And the value of cosine is this value right here. This is EP. So total value gives you minus 40 EP meters per second. Okay? So now we can move on. This is the influence of segment 1. Let's move on to segment number 2. Segment number 2, this is theta 2. This is theta 2. This is 5. This is 4. Square root of this is 25 plus 16. That gives you square root of 41. So cosine of theta 2 will be 5 divided by square root of 41. And we know that VP for this segment will give you 2 pi, because the angles are the same. So I just used the following, the same expression I used in the previous chart. And that gives you minus 200, 2 pi divided by 4, 5 over square root of 41 EP. And VP2, for you do the whole calculation, gives you 6.21 EP meters second. Okay, so we are done with segment number 2. Let's move with triangle number 3. This triangle, remember that the angles were completely different. So these angles were identical. Here the angles are different, so I need to do this one separately. So here, what we know, this is 5. This is this angle was, this distance was this is 5. This is 6. This angle is theta 2, and then again this is square root of 61, and the total angle P3 will equal to minus gamma 4 pi h. The 4 pi h is correct, because we are not considering this segment here. We are just considering half of that. So this is cosine of theta 2, EP, and this will be minus 204 divided by the distance from here. Where I'm really interested, this is like here, and the distance is, we are doing this location, so sorry. So we are looking for the angle here, and the total distance is 5. As you can see, this is the distance perpendicular. This is 6 over square root of 61 EP. So VP3 will be minus 2.05 EP meters per second. Okay? So now let's move on. We got this one. Let's move on to the next triangle. The next triangle I chose was triangle number 4. This triangle right here. This is the location I want to find everything. 5, 4, and again you can do the math here. This is the angle alpha that we call alpha. And then from the equations I just showed you at the beginning, this gives you 4 pi cosine of alpha EP, and this will be minus 200, 4 pi. The distance from here to here perpendicular is 5. Cosine of alpha will be 4 over square root of 41. You can see the adjacent over here, hypotenuse. 4 divided by square root of 41 EP. So VP4 will be minus 3.11 EP meters second. So that is segment number 4. So we got 1, 2, 3, 4. Let's do 5 and 6. 5 or 6 are kind of symmetric as the previous one, but let's just do it anyways. So this is the location I'm looking for. This is the distance perpendicular. This is 5. This is 4. This is come from the geometry. This is square root of 41. So VP5 is equal to minus. This is 4 pi h cosine of theta 2 EP is equal to minus 200 4 pi 4 over square root of 41 EP. So this segment 5 will give you minus 3.11 EP at that point. That is point number 5. Let's go. We got 1, 2, 3, 4, 5. Let's go to the last segment. The location I'm really interested in. This location right there. That location gives me the following values. This is distance perpendicular to this. This is alpha. This is 6. This is 5. This is square root of 61. So going back to the equation, just half of that triangle gives you 4 pi h cosine of alpha EP minus 200 4 pi 6 and then cosine of alpha gives you 6 over 61. This is adjacent over hypotenuse. And so VP6 gives you minus 2.04 EP meter second. So at the end of the day, now we add all the contributions together. And to add the contributions, we find that this whole thing gives you VP is equal to minus, it gives you minus 3.40 plus minus 6.21 minus 2.04 minus 3.11 minus 3.11 minus 2.04, and this whole thing gives you minus 1991 EP. The total velocity then in meters second squared is given by this. That is the velocity at point P due to all the vortices acting in the surfaces right here. So this concludes example number 1.